Hello there, and welcome to the Sleepy History Channel. Tonight, we step into one of the most secret and world-changing efforts ever undertaken, one that unfolded behind fences, inside guarded laboratories, and beneath desert skies. This is the story of the Manhattan Project, the race to build the atomic bomb. It is a story of brilliant minds drawn together by fear and urgency. It is a story of hidden cities that appeared almost overnight, of rivers harnessed for cooling reactors, and of calculations that reshaped the fate of nations. Before a single flash lit the New Mexico desert, there were letters that carried warnings, trains that carried strange cargo, and conversations that could not be repeated. The project fused science, industry, and military command into something entirely new. It gave birth to the atomic age, and it forced humanity to confront power on a scale never before imagined. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, there is nothing you need to do. Let your shoulders soften, allow your jaw to unclench, and let your breathing slow as we drift back into a time of guarded doors and glowing horizons. Let's begin. The Manhattan Project built the first atomic bombs in total secrecy. Imagine creating a world-changing weapon while hiding it from neighbors, journalists, and even most of the people helping you build it. That was the daily reality. Whole facilities appeared behind fences and guard towers, and many workers knew only the small step directly in front of them. A machinist might shape metal parts without being told why precision mattered so much. A chemist might test samples without being told what the samples were. Mail was monitored, conversations were cautious, and maps simply left places off the page. Even the project's name worked like a curtain, because it sounded like paperwork, not a revolution in physics. The secrecy was not just a policy. It became a culture, one that wrapped around thousands of lives until the moment the world finally heard the news. It became the most expensive scientific project of the Second World War. This was not one laboratory with clever chalkboards. It was an industrial empire built at wartime speed. The work demanded massive buildings, specialized machines, new supply chains, and rivers of electricity that had to be generated and delivered reliably. Entire teams designed equipment that had never existed before. Then other teams built it, maintained it, and rebuilt it when it failed. Trucks, trains, and guarded shipments moved materials across the country in carefully timed waves. Administrators tracked resources like a battlefield, because delays meant vulnerability. The cost was not only money. It was talent pulled from universities, factories redirected from other needs, and communities reshaped overnight by urgent construction. What makes it staggering is that the spending was aimed at a single goal: to force nature's smallest forces into something the world could not ignore. Spies inside the program quietly carried secrets to the Soviet Union. Even with guards, badges, and strict need-to-know rules, information leaked. Some people felt ideological loyalty to an ally, but was also a future rival. Others believed that nuclear knowledge should not belong to only one nation. A few were persuaded by handlers who understood how to exploit loneliness, pride, or fear. The most damaging spying did not require stealing a finished bomb. It required passing design logic, research results, and production details that saved years of effort. Messages moved through coded meetings and discrete drops, often in ways that looked like ordinary life. The project's leaders suspected leaks at times, yet the scale of the work made perfect control impossible. What makes this story chilling is the quietness. While engineers argued over materials and timing, a second invisible effort was also underway, moving ideas across borders without a single explosion. The result helped shape a world where more than one power held the same terrible key. It began as a fear that Nazi Germany might build a bomb first. In the early years, the terrifying part was not what the Allies could build. It was what they might face. Physicists understood that splitting atoms released immense energy, and they also knew that Germany had brilliant scientists and a ruthless government. Rumors traveled faster than proof, and every rumor felt like a ticking clock. A single breakthrough on the other side could change battle plans, alliances, and the very idea of survival. That fear turned abstract theory into an emergency, and it pushed cautious academics toward wartime decisions. It also created a strange urgency, because nobody could pause to confirm everything. They had to act, while uncertainty still lingered. The project's origin story is not just invention. It is a race powered by dread, where imagination and intelligence both pointed toward the same unacceptable possibility. A letter from Einstein helped push the United States toward action. A famous scientist did not build the bomb, yet his name helped open the door. The key moment was a warning carried to the highest levels of government, arguing that uranium might produce a new kind of weapon. The letter was brief compared to the storm it helped create, because it framed the stakes in plain terms for people who did not live in physics. It suggested that research could no longer remain a quiet academic pursuit, since war was already reshaping what science might become. The message did not instantly create the massive program that followed, yet it helped shift attention and funding toward atomic work. It also shows how influence can travel. A page of carefully chosen words can move faster than factories. It can change what leaders fear, and what they decide must be built before an enemy builds it first. Its director, Leslie Groves, ran science like a military campaign. He arrived with a general's mindset and a builder's impatience. He demanded schedules, clear chains of command, and answers that could survive pressure. Scientists were used to debate and uncertainty, yet he treated delay like a strategic threat. When equipment failed or designs changed, he pushed for solutions that were practical, not elegant. He also understood that morale mattered, so he backed the people he trusted and removed obstacles with startling speed. His role was not to solve equations. It was to make sure that land was purchased, plants were built, power was delivered, and security held. In that way, he turned discovery into production. The project needed visionaries, but it also needed someone who could say, "Build it now," and mean it. His leadership shows how wartime urgency can reshape how knowledge is managed, funded, and forced into reality. J. Robert Oppenheimer led Los Alamos with brilliance and fragile intensity. He was not the safest choice on paper, yet he became the human center of the laboratory. He could speak to theorists in their own language, then turn and translate problems for engineers who needed workable designs. People described his mind as quick and wide, as if he could hold many arguments at once without dropping them. That gift mattered, because the work required constant synthesis between new physics and stubborn hardware. Still, the pressure left marks. Long days blurred into nights, and the stakes pressed inward, because every calculation carried the weight of cities and wars. He inspired loyalty, and he also radiated strain. The leadership at Los Alamos was not calm management. It was a high-wire act, balancing imagination, coordination, and fear. In that sense, his story is a reminder that breakthroughs often come through people who feel everything too sharply and keep going anyway. Thousands worked on tiny steps without knowing the final purpose. Most people never saw a bomb design, and many never heard the word atomic. They were assigned a task, trained to do it well, and told that questions were dangerous. One person might tighten bolts on a pipe system all day. Another might test samples, record readings, and hand the results to a supervisor who offered no explanation. This compartmentalization made secrecy possible, yet it also made the work surreal. You could pour years of effort into something you could not describe to your spouse. Pride and frustration lived side by side because you sensed importance, but you could not name it. The project became a giant puzzle where most hands held only one piece. That structure shaped behavior. People focused intensely on small details because the mission was invisible but urgent. It is one of the strangest features of the project that a world-changing outcome was built from countless workers who never knew what they were building. Many workers believed they were simply building ordinary war materials. That belief did not require deception with elaborate stories. It happened naturally because wartime factories were everywhere, and secrecy made unusual work feel routine. A person could assume they were producing components for aircraft, radios, or artillery. The language around them reinforced that impression, since supervisors used vague terms and avoided specifics. Even the scale could be misunderstood because large plants were common during the war. The difference was hidden in what the machines were actually doing, which was separating isotopes, handling exotic chemicals, or preparing metals that few people had ever heard of. Some workers later said they felt a jolt of recognition only when the news broke, because suddenly their long shifts had a name. Until then, they measured success by safety, speed, and meeting quotas. This creates a powerful contrast. The most extraordinary weapon in history was built inside the emotional atmosphere of an ordinary job, with lunch breaks, sick days, and paychecks, while the dalana, true purpose, stayed locked behind a closed door. Security used code names, badges, and constant compartmentalized information. Everyday life was organized around who you were allowed to be and what you were allowed to know. Badges controlled where you could walk, and the wrong door could bring questioning. Code names turned places and materials into neutral labels, which helped prevent accidental slips in casual conversation. Meetings were limited, documents were tracked, and even trash could matter. People learned to speak in careful generalities because clarity could be dangerous. This system did more than prevent espionage. It shaped relationships. Co-workers might share a cafeteria table while holding completely different pieces of the same mission, with no permission to connect them. It also created a constant low hum of vigilance, where small mistakes felt heavy. Yet security was never perfect, because no system can fully control human curiosity and human carelessness. The fascinating tension is that the project depended on creative minds, and creativity does not thrive under constant suspicion. The program had to guard its secrets while still letting ideas flow, and that balancing act became part of its daily drama. Even the word plutonium was once unknown to most participants. Today it sounds like a familiar symbol of the nuclear age, yet at the time it was a new element with a new name. Many people in the project were handling materials without being told what they were called, or what made them special. That secrecy created a strange linguistic world where ordinary words were avoided and technical terms were restricted. Even when someone did hear the name, it might arrive without context, like a label on a crate rather than a concept in a textbook. The element itself was mysterious because it did not exist in nature in usable quantities, and it had to be created inside reactors. That meant it carried an aura of human-made power. The name began as a scientific designation, yet it quickly became a kind of loaded word, hinting at transformation and danger. This is one of the quiet marvels of the project. It was an era when an entirely new substance entered human history, and most of the people helping to produce it were not permitted to speak its name aloud. A single missing notebook could trigger interrogations and tightened rules. In a place built on secrecy, paper was never just paper. A notebook could contain a half-formed idea, a measurement, or a sketch of a device. It could also contain enough context to connect separate pieces of the puzzle. That is why a lost notebook could set alarms ringing. Security teams would trace who had access, who was present, and who might have seen it last. People could be questioned sharply, not because they were guilty, but because the risk was too great to ignore. The atmosphere could shift overnight, from routine pressure to a new level of constraint. Rules would tighten, checkouts would become stricter, and reminders would echo through offices and workshops. This kind of incident reveals how fragile control can be. The entire project depended on keeping information contained, yet information has a habit of wandering. Sometimes it wanders through malice, and sometimes it wanders through simple human forgetfulness. In that sense, the project was always balancing on the edge of its own paperwork. Hanford was chosen for space, water, and distance from cities. Choosing Hanford was like choosing a blank page that could hold an entire industrial experiment. The site offered wide-open land where huge buildings could rise without prying eyes, and it sat far from major population centers if something went wrong. Planners also wanted room for security buffers, rail access, and future expansion, because nobody knew how many reactors or processing facilities would be needed. The region's isolation made construction harder, yet it also made secrecy easier. Thousands of workers arrived, roads appeared, and a fenced world took shape at high speed. Hanford became a place where planners could think in massive scale, not just in laboratory scale. That choice mattered because reactor production was not a single device. It was a continuous industrial process with hazards that demanded distance, planning, and control. The landscape itself became part of the technology. The Columbia River cooled reactors that ran day and night. A nuclear reactor does not pause when people are tired, so its cooling system cannot pause either. At Hanford, the Columbia River became a critical partner, providing the water needed to carry heat away from the reactor core. That cooling flow had to be reliable and carefully managed, because too little water could mean overheating, and sudden changes could stress equipment. Engineers designed intake structures, pumping systems, and monitoring routines that treated water like a lifeline. The river's steady availability made continuous production possible, which was essential for generating plutonium on a tight wartime schedule. Yet using a powerful river also raised constant questions about temperature, contamination, and how to measure safety in a new kind of industry. The eerie part is the contrast. The river looked timeless and calm, while nearby machines were changing atomic identities inside sealed metal channels. A familiar landscape was supporting an unfamiliar power. A hidden desert test called Trinity proved the bomb could work. In a remote stretch of New Mexico, the project had to answer one terrifying question. Would the implosion idea actually ignite a nuclear chain reaction, or would it fail in an expensive flash? Engineers built a tower, wired miles of cables, and rehearsed timing again and again, because a fraction of a second mattered. Scientists planned measurements for light, heat, pressure, and radiation, even though the event would unfold faster than a human blink. Crews worried about weather, because wind could spread fallout in the wrong direction. Soldiers guarded the roads, and observers waited at distant points with special goggles and instruments. When the device detonated, the landscape briefly became brighter than day, and the team finally had proof. The war had a new weapon. The future had a new shadow. Los Alamos rose fast, turning mesas into a laboratory city. On a high plateau, a quiet school site became a place where some of the 20th century's sharpest minds lived behind checkpoints. The location was chosen for isolation, but isolation created its own strange world. Scientists arrived with families, books, and half-finished ideas, then found themselves in temporary housing and hurriedly built offices. They held lectures, argued over equations, and still stood in line for supplies like everyone else. The town ran on rationing, improvisation, and constant hurry. Work days stretched, but so did the need to feel human. So there were small concerts, hikes, and moments of laughter that felt almost forbidden. Everything important was guarded, yet the real intensity lived inside the minds of people trying to make the impossible reliable. A city formed from urgency, where daily life and world history shared the same narrow roads. Entire industrial towns appeared just to enrich uranium. To turn rare uranium into bomb fuel, the project did something astonishing. It built places that existed largely for one hidden purpose. Oak Ridge grew into a landscape of factories, pipes, and humming equipment, all devoted to separating nearly identical atoms. Workers poured in from across the country, moved into new housing, and learned routines that felt ordinary even when the mission was not. Some people ran machines by watching gauges, adjusting controls and reporting numbers, without being told what those numbers truly meant. The plants demanded enormous power because the process pushed against nature's stubborn saneness. Materials corroded, parts failed, and fixes had to be invented midstream. What sounds like a simple phrase, enrich uranium, required a whole ecosystem of engineering, logistics, and human labor. It was a modern alchemy town, built fast, kept quiet, and aimed at one narrow slice of matter. Hanford's reactors made plutonium from uranium, one atom at a time. While one part of the project chased rare uranium, another part created a new material by transforming atoms inside reactors. At Hanford, huge machines ran with relentless steadiness, and their job was to produce plutonium within uranium fuel. The work depended on careful control, because reactors build heat and radiation even when everything seems calm. Water was essential for cooling, and engineers designed systems that could keep flowing under constant strain. After irradiation, the fuel had to be processed chemically, and that meant handling substances that could harm you without any warning smell or visible sign. Remote tools and thick shielding became everyday companions. Hanford was industrial-scale physics, where the raw ingredient moved from solid metal to something far more potent. The mind-bending part is the timeline. A reactor could quietly run for days, and inside it, the elemental identity of matter was changing, invisibly, patiently, and forever. Two rival bomb designs raced forward under the same urgent deadline. The project did not bet on a single approach. It pursued two very different paths at once, because the clock was unforgiving. One design relied on a straightforward idea: bring pieces together quickly enough to start a chain reaction. The other design demanded perfect symmetry, squeezing material inward with explosive force so it became briefly denser and more reactive. That second path was a nightmare of timing, because many detonators had to act almost together. If they did not, the weapon could fail. This split strategy created tension because teams needed resources and attention, and nobody wanted their approach to be the one that missed the moment. Meetings could feel like races disguised as discussions. The fascinating twist is how the rivalry helped. Different designs forced different experiments, different instruments, and different kinds of creativity. Under pressure, the project became two parallel stories of ingenuity, each pushing the other to move faster. Scientists feared a runaway chain reaction could ignite the atmosphere. Before the first full-scale test, some people asked a question that sounds like science fiction. Could a nuclear explosion trigger further reactions in the air, spreading in a self-sustaining way? The fear was not casual panic. It came from the fact that the project was exploring a regime of energy release that nobody had ever observed. Physicists ran calculations, argued assumptions, and checked one another's reasoning, because the stakes were literally global. The conclusion was that the atmosphere could not be ignited in that way, based on how nuclei behave and how energy spreads. Still, the very fact that serious people considered it tells you how unknown the territory felt. They were building a device that turned mass into heat and light with startling efficiency, and they could not lean on history for reassurance. It was a moment where mathematics had to provide calm, and where confidence still carried a tremor underneath. The project changed world politics in days, and shaped decades afterward. Once the weapon existed, diplomacy changed its language. Allied leaders could negotiate with a new kind of leverage, because the promise of overwhelming force now sat behind every conversation. After the bombs were used, nations around the world understood that war had entered a different era, one where a single mission could destroy a city. Governments began reorganizing science under national security, and secrecy expanded into peacetime. The idea of deterrence took hold, built on the grim logic that fear might prevent conflict. At the same time, calls for international control rose because uncontrolled competition felt like a path to catastrophe. The atomic age did not arrive slowly. It arrived like a door slammed open, and the world had to step through it. The project's legacy shows up in alliances, crises, treaties, and the constant background awareness that technology can outrun wisdom if urgency is allowed to curl. Led. The project spanned multiple states, with sites linked by guarded convoys. It was never one secret building. It was a hidden network, stitched across the country like a second map beneath the public one. Ore, chemicals, machine parts, and documents moved along rail lines and highways with quiet urgency. Many shipments looked ordinary, yet guards treated them like crown jewels. Drivers followed strict routes, and schedules were designed to reduce curiosity and risk. A delay could ripple outward, because one site depended on another site's output, and that dependency never slept. Even paperwork became a kind of cargo, carried by couriers who understood that a single page could be more valuable than a crate of metal. This sprawling geography created a new kind of coordination. It was science that needed logistics, and logistics that demanded secrecy. The result was an invisible nation within a nation, connected by motion and silence. Uranium ore traveled from mines to mills to secret refining plants. The journey started as rock that looked almost ordinary, yet it carried a hidden promise of enormous energy. Miners dug it out, mills crushed it, and chemists coaxed the uranium into a more concentrated form that could be shipped again. Each step changed the material's identity, from heavy stone into powders and compounds that could enter the project's factories. What made the pipeline so gripping was its scale and its caution. Shipments had to be tracked, guarded, and kept moving, because every delay slowed work elsewhere. The material also came from different sources, which meant variable purity and different chemical headaches. Teams learned to think like both geologists and manufacturers, because nature did not deliver uniform ingredients. In the end, the bomb's story begins long before the laboratory, with a supply chain that turned raw earth into a strategic resource. Oak Ridge used gaseous diffusion, forcing uranium through endless barriers. The idea sounds simple until you picture it. A gas made from uranium was pushed through porous barriers, and the lighter molecules slipped through just a bit more often than the heavier ones. That tiny advantage was repeated again and again through stage after stage, like climbing a mountain with steps so small you almost cannot see progress. The barriers had to be uniform and strong, because a defect could ruin separation and waste precious time. pumps and compressors worked constantly, and the system demanded relentless maintenance. Workers had to keep pressure stable and temperatures controlled because the process was sensitive and unforgiving. What makes it fascinating is how it turns a subtle difference in mass into a national-scale machine. It was physics translated into plumbing and pressure, with patience as the real fuel. The final enriched product was not created by one dramatic moment. It was created by persistence multiplied thousands of times. Oak Ridge also used electromagnetic separation, like giant industrial mass spectrometers. Instead of pushing gas through barriers, this method steered charged particles through magnetic fields. When uranium ions moved through the magnets, their paths curved, and the slight difference in mass made their arcs separate. That separation was then collected, scraped, and processed, often in quantities that looked almost laughably small compared to the effort. The machines were enormous, yet the product could arrive as a thin deposit that had to be carefully recovered. Operators watched readings, adjusted settings, and kept the system stable because a drift could ruin hours of work. The method demanded both precision and endurance. Magnets had to hold steady, vacuum systems had to behave, and the equipment needed constant attention. What feels magical is the translation. A principle from physics classrooms became a row of industrial machines that could sort atoms by weight, as if matter had lanes on a track. Calatrons consumed staggering electricity, drawing power like a small city. These machines did not sip energy. They drank it. To bend and control charged particles at scale, the magnets demanded enormous current, and that turned electricity into a strategic ingredient. Power plants had to feed the process reliably because interruptions wasted output and strained equipment. The hum of energy was part of the method's character, as if the building itself was breathing with the grid. This appetite affected planning in surprising ways. Engineers had to consider heat, cooling, and insulation because high currents create their own hazards. It also meant the project competed with other wartime needs, so power allocations mattered. What makes the Calatron so memorable is the contrast. The goal was a microscopic separation of isotopes, yet the pathway required thunderous industrial strength. It is one of those moments in history where you see how modern science can demand not only ideas but infrastructure, generators, and miles of cable. Some operators were young women trained to watch dials and needles. In a room filled with machines, the project relied on eyes and attention. Many operators were young women recruited and trained to run complex equipment through observation and careful adjustment. They learned patterns in the instruments, the slight tremble that hinted something was drifting, and the steady behavior that meant the system was behaving. The work required patience and focus because the machines could run for long stretches, and a small mistake could spoil a run. What is striking is how the training was practical rather than theoretical. They did not need to be told the deep physics. They needed to keep the process stable and productive. In a world where secrecy limited explanations, skill still emerged through repetition and responsibility. This detail opens a wider story. The atomic program was not only famous scientists. It was also thousands of workers whose careful hands and steady minds made the machines do what the equations demanded. Their dial skills outperformed many physicists without the math behind it. A physicist could explain why the machine should work, yet a skilled operator could often sense trouble before anyone else. Over time, some operators developed an almost musical relationship with their instrument panels. They recognized the look of a healthy run, and they noticed tiny deviations that signaled a problem in the making. This was not mystical talent. It was learned intuition, built through hours of watching, adjusting, and seeing the consequences. In some cases, supervisors noticed that certain operators consistently produced better results, even when they could not describe the underlying theory. That gap is fascinating because it shows two kinds of expertise living side by side. One kind lived in equations and predictions. The other lived in attention and craft. It also reveals a quieter truth about big projects. Breakthroughs depend on people who can keep complicated systems steady, even when they never receive the full story of what the system is meant to become. The enrichment process demanded patience, because tiny differences mattered hugely. In everyday life, a tiny difference feels insignificant. In isotope separation, it becomes everything. The methods used at Oak Ridge worked by amplifying a small advantage over and over, which meant progress came in slow, disciplined increments. That demanded a particular mindset. You had to trust the process while results arrived gradually. You also had to guard against complacency, because long runs can tempt people to relax, and that is when errors appear. Maintenance became a rhythm, inspections became habits, and record-keeping became a form of survival. The stress was not only technical, it was psychological. The war demanded speed, yet the physics demanded repetition. This tension shaped the culture of the plants. People learned that the quickest path was often the one with the fewest mistakes, even if it felt slow in the moment. When the enriched material finally accumulated, it carried the weight of countless small choices made correctly, hour after hour. One useful uranium isotope was rarer than intuition would suggest. Most people hear uranium and imagine a single substance, yet the element comes in slightly different forms that behave differently in nuclear reactions. The isotope needed for a bomb is present only as a small fraction of natural uranium, which turns get uranium into separate a needle from a haystack. That scarcity explains the scale of the enrichment plants and the urgency behind multiple methods running at once. It also explains why every gram mattered. A tiny loss in processing could mean a meaningful setback, because the starting supply was already thin. This rarity shaped strategy because it forced planners to think in terms of throughput and yield rather than dramatic discoveries. It is a reminder that history can hinge on proportions. The difference between success and delay was not only ingenious. It was in the stubborn fact that nature does not offer the needed isotope in convenient abundance. The project had to manufacture rarity into availability, which is one of its most mind-bending achievements. Engineers had to invent materials that resisted corrosive uranium hexafluoride gas. To separate uranium by diffusion, it had to be turned into a gas, and that gas was chemically aggressive. It attacked many common materials, which meant pipes, seals, and valves could fail in ways that were dangerous and costly. Engineers faced a challenge that was as much about chemistry as it was about physics. They had to find metals, coatings, and gasket materials that could survive long exposure without crumbling, swelling, or leaking. Each choice mattered, because a material that worked in a small test might fail in a sprawling plant under constant pressure. Factories also had to produce these parts at scale, with consistent quality, because inconsistency created weak points. This material problem is fascinating because it shows how advanced science can be stopped by something as humble as a seal. The bomb did not depend only on clever theory. It depended on whether a valve could keep its integrity when a harsh gas tried to eat its way out. Leaks and contamination turned routine maintenance into a constant battle. In an enrichment plant, maintenance was not a quiet background task. It was a fight against wear, vibration, chemical attack, and the sheer complexity of miles of equipment. A small leak could reduce efficiency, damage machinery, and create safety hazards. Crews had to locate problems, isolate sections, and repair them without disrupting more of the system than necessary. Even cleaning carried risk, because residues could contaminate areas that were meant to stay controlled. Tools, clothing, and procedures had to follow strict routines, since careless handling could spread trouble and slow production. The tension came from priorities that pulled in opposite directions. Fix it fast, and also fix it safely. Keep the plant running, and also stop the leak before it grows. This is where the drama becomes very human. The work was not only about invention, it was about persistence under pressure, with teams solving practical crises day after day, so the larger mission could keep moving forward. Building reactors required unfamiliar chemistry, metallurgy, and radiation safety. Reactor building forced experts to step outside their comfort zones. Physicists could predict neutron behavior, yet reactors also demanded materials that would survive heat, stress, and radiation for long stretches. Chemists had to think about corrosion, water purity, and how tiny impurities could affect performance. Metallurgists faced questions about swelling, cracking, and how metals change under conditions that ordinary factories never see. Safety teams also had to invent practices for radiation exposure, monitoring, and protective routines, because there was no long history to rely on. People learned by doing, and sometimes by being startled. Instruments were developed, warning signs became part of the scenery, and procedures tightened as experience grew. The most fascinating part is how interdisciplinary it became. A reactor was not a physics device alone. It was a living system of materials, fluids, heat, and human judgment, all working together to keep a chain reaction under control. Early reactor parts swelled and warped under intense neutron bombardment. Inside a reactor, neutrons are not gentle. They slam into materials and slowly change them, which meant early components could behave in ways that surprised even experienced engineers. Parts that looked solid and stable could swell, shift shape, or become brittle over time. That created a mechanical problem and a psychological one. If a component deformed, it could change cooling flow or make maintenance dangerous, and it could also threaten confidence in the whole design. Teams had to track subtle changes, compare measurements, and redesign parts so they could endure longer operation. The challenge was compounded by secrecy and speed, because fixes had to be developed quickly and often with limited outside advice. This is one of the most revealing realities of the project. Nature was not only being harnessed, it was pushing back through materials science. The reactors taught engineers that the atomic world can reach out and reshape the tools built to control it. Cooling failures could overheat fuel, creating terrifying risks inside the core. A reactor's heat is not like a normal furnace, because it comes from the heart of the fuel itself. If cooling flow faltered, temperatures could climb fast, and rising heat could damage fuel and surrounding structures in dangerous ways. That possibility haunted the design process. Engineers built redundancies, alarms, and operating limits, and they trained staff to treat minor irregularities as serious warnings. The fear was not theatrical. It was grounded in the reality that you cannot see the hottest region directly, and you cannot touch the problem once radiation levels rise. Operators had to trust instruments, interpret patterns, and respond quickly without panic. Even routine events like pump maintenance carried weight, because a mistake could cascade. The tension of reactor work came from its quietness. Most of the time, everything seemed stable. That calm was exactly why vigilance mattered. In a system this powerful, trouble could begin silently and then become urgent. Plutonium was separated with chemical plants that handled deadly radioactivity. After irradiation, the fuel was not useful until plutonium could be extracted, and that required chemical processing at an unsettling scale. Imagine a factory where the raw material is intensely radioactive, where direct handling is dangerous, and where contamination can spread through a single careless car. Step. The separation plants used carefully designed chemical pathways to dissolve, react, and isolate the desired element from a mix of other substances. This was not chemistry done with small beakers on a bench. It was chemistry done with large vessels, piping, shielding, and procedures that had to anticipate spills, fumes, and radiation exposure. Workers relied on protocols, protective gear, and remote techniques because safety was not optional. The gripping part is the mixture of routine and hazard. People still had shifts, checklists, and equipment inspections. Yet the consequences of an error were far higher than in ordinary industry. These plants turned reactor output into bomb material, one controlled reaction after another. Workers used remote manipulators because some rooms were too hot to enter. Some spaces inside the processing facilities were so radioactive that entry was not just risky, it was impossible. To work there, crews used remote manipulators, mechanical arms controlled from behind shielding. These devices let people grasp tools, turn valves, and move objects without being in the same room as the hazard. It sounds straightforward until you picture the difficulty. Depth perception changes behind thick windows, movements feel delayed, and even a simple task can become clumsy. Workers trained like craftsmen, learning how to feel through metal joints and cables. When something broke, repairs could become a puzzle, because the broken thing was also dangerous to approach. This created a strange kind of workplace heroism, focused not on dramatic gestures, but on steady hands and problem-solving. Remote manipulators also changed the relationship between humans and machines. People were building world-changing material while standing at a distance, guiding tools as if they were puppets, because the air itself could harm them. The first reactor went critical, meaning it sustained its own chain reaction. When a reactor goes critical, it crosses a threshold from temporary activity to self-sustaining behavior. It is a moment defined by balance, because the goal is not runaway power. The goal is controlled continuity. At Hanford, reaching that point meant that design choices, construction work, and careful planning had finally aligned. Operators watched instruments closely, because the change is measured by signals, not by visible flame. The event carried emotional weight for people who understood what it meant. A controlled chain reaction was proof that humans could organize neutrons into an obedient pattern, and that pattern could be sustained long enough to produce new materials. It was also a reminder that control must remain control, minute after minute. Once you have a critical reactor, you have a system that can keep going, and therefore a system that must be watched without lapse. The milestone was scientific, industrial, and deeply unsettling all at once. That moment was quiet, but it marked a new human power. There was no marching band when the reactor entered its steady state. There was just a set of readings, a room of people paying attention, and the knowledge that something irreversible had happened. Humans had learned not merely to observe nuclear forces, but to guide them in an ongoing way. This was different from a brief experiment. It was a continuous capability, which meant it could be scaled, replicated, and woven into plans. Quiet moments like that are often the most powerful in history, because they arrive without drama and then reshape everything afterward. In that silence, people confronted a strange mix of pride and unease. The accomplishment was technical and immense. It also carried a new moral and political reality, because sustained nuclear reactions could lead to weapons and to other uses that would follow after the war. The calm of the control room stood in sharp contrast to what that new power could eventually do. Reactor fuel arrived in regular batches, like an assembly line for atoms. To keep production steady, fuel had to move through the system in a planned rhythm. Fresh fuel was prepared, loaded, irradiated for a set period, and then removed for processing. That repeating schedule turned the reactor into a kind of atomic factory line where time inside the core was part of the recipe. Managers tracked batches, operators monitored conditions, and downstream facilities prepared to receive the irradiated material on cue. This cadence mattered because the reactor was not making a finished product in one step. It was making a starting point that still needed careful extraction. Regular batches also created pressure to avoid interruptions, because a delay in fuel movement could disrupt multiple linked operations. The fascinating part is how industrial it became. We often imagine nuclear work as a single flash of discovery, yet here it was, a steady pipeline with routines and deadlines. The project built a workflow where atoms were processed with the logic of manufacturing, and that workflow helped turn theoretical physics into wartime output. The Hiroshima bomb used a gun-type design, simple but material-hungry. The weapon dropped on Hiroshima relied on a blunt, almost mechanical idea. 2 subcritical pieces of uranium were kept apart. Then a conventional explosive drove one piece into the other inside a long barrel. The appeal was reliability. If the parts met fast enough, the chain reaction would begin, and there were fewer moving mysteries than with more complex approaches. That simplicity came with a steep price. It demanded a large supply of highly enriched uranium because the design was not stingy with its fuel. It also had to be engineered to survive violent acceleration without jamming, misaligning, or tearing itself apart. In a strange way, it was both straightforward and unforgiving. Everything depended on timing, alignment, and the quality of the uranium. A single concept carried the weight of an enormous industrial effort. The Nagasaki bomb used an implosion design, harder but more efficient. The Nagasaki weapon pursued elegance under pressure. Instead of firing 2 pieces together, it used a shell of explosives to crush a plutonium core inward from all sides, raising its density until it could sustain a Proul chain reaction. The design was far more demanding, because any unevenness could spoil the compression and waste the precious material. Yet it offered a powerful advantage. It needed less fissile material to reach the same terrible threshold, which mattered when plutonium production was limited and chemically complex. Implosion also demanded a deep marriage between theory and craft. Physicists had to predict how matter would behave in an instant, and engineers had to shape explosives so the real world matched the math. It was an invention that lived in microseconds, yet it required months of testing, machining, and careful assembly before it could be trusted. Implosion demanded explosive lenses shaped with extreme precision. To squeeze the core evenly, the blast had to arrive like a perfectly timed inward wave. Ordinary explosives produce messy fronts, so the team invented explosive lenses. These were carefully shaped blocks that combined fast and slow explosives, guiding the detonation into the right geometry. Think of them as sculpted timing devices made from chemicals. Their shapes had to be manufactured with care, because a small defect could distort the wave and ruin the symmetry. They also had to be assembled like a 3-dimensional puzzle, with each piece meeting its neighbors cleanly. This work demanded new standards of quality, and it demanded trust between people who spoke different professional languages. Chemists controlled explosive behavior. Machinists shaped the pieces. Test crews proved whether the wave looked right. The remarkable part is that a weapon's success depended on crafting explosions that behaved with the discipline of clockwork. Teams tested dozens of lens shapes, chasing symmetry in microseconds. Getting implosion right was not a single breakthrough. It was a long sequence of trials where each test asked one question. Did the shock arrive evenly? Did it speed up or slow down in the wrong place? Did the geometry wobble? Teams tried different shapes, different explosive pairings, and different assembly methods, then looked for patterns in the results. Some tests were small-scale, designed to reveal the wave's shape without using precious nuclear material. Others pushed closer to full conditions because only realistic pressures expose certain flaws. The emotional strain was constant. A design that looked promising could fail for a reason no one had predicted. When that happened, the group had to revise the lens, adjust the detonator placement, and try again. All of this happened while the war pressed forward. Symmetry became an obsession, because in implosion, symmetry is not beauty. It is survival for the design. High-speed photography captured shock waves too fast for human sight. The implosion wave moved at speeds that made ordinary observation useless. So the project leaned on high-speed photography, using special cameras and timing systems to freeze events that unfolded in a fraction of a blink. A test might look like a flash and a puff to the naked eye, yet the photographs could reveal the shape of a shock front, the timing of a collapse, and the moment a casing deformed. These images were not taken for drama. They were taken as evidence. Engineers could compare one frame to a model, then decide what to change next. Lighting, triggers, and protective housings all had to be designed, because the blast environment destroys delicate equipment. The fascinating part is that a camera became a scientific instrument, almost like a microscope for violence. It let humans study explosions as if they were slow enough to understand, and that understanding was essential for making an implosion system repeatable. Detonators had to fire almost simultaneously, or the core would fizzle. In an implosion device, a timing problem is brutal. Multiple detonators must begin their work so close together that the resulting shock arrives as a unified inward push. If one detonator is late, the wave becomes lopsided. Compression suffers, and the core may never reach the conditions needed for a full chain reaction. That outcome is called a fizzle, and in wartime terms it meant catastrophic failure. Achieving near simultaneity required precision engineering, careful wiring, and rigorous testing of the detonators themselves. It also demanded confidence under stress, because the system was only as strong as its weakest connection. People learned to treat tiny electrical differences as major threats, since a small delay could echo into a large asymmetry. This is one of the most startling aspects of the project. The difference between a world-changing blast and an embarrassing dud could be a sliver of time that no human senses directly. The bomb's timing involved microseconds, but the consequences lasted generations. The chain reaction in a nuclear weapon races through its critical phase in a tiny fraction of a second. In that brief window, matter changes state, energy floods outward, and the surrounding world is rewritten. It is almost impossible to hold both truths in the mind at once. The action is swift beyond intuition, yet the effects stretch forward through history. Military strategies adjusted, diplomacy gained a new tension, and societies began living with a background awareness that did not exist before. The scientific community was also reshaped. Some researchers carried pride, others carried regret, and many carried complicated mixtures of both. Families of workers looked back and realized that their guarded years had helped create something that could not be put back into secrecy. The timing lesson becomes almost philosophical. Human decisions can ignite processes that unfold faster than we can think, then ripple outward through politics, culture, and memory for decades and more. The core used a neutron initiator to start the chain at peak compression. In an implosion design, the chain reaction must begin at the right moment. Too early, and the core is not dense enough, which wastes the compression. Too late, and the core begins to rebound, which also wastes the opportunity. To solve this, designers used a neutron initiator placed at the center, intended to provide a burst of neutrons when compression reached its peak. The idea sounds neat and tidy, yet it demanded delicate engineering. The initiator had to survive assembly, remain stable, and then perform reliably in a violent environment. It also had to fit into the overall timing plan, where shockwaves, detonators, and material behavior all converged. This detail is fascinating because it reveals how controlled the process had to be. A nuclear weapon is not only raw power, it is choreography. The initiator was a cue in that choreography, meant to ensure the reaction began at the most destructive instant. Scientists built new instruments just to measure the bomb's brief physics. You cannot improve what you cannot measure, and the bomb's key events were nearly too fast to study. So teams created instruments that could survive blasts long enough to record signals, and then deliver those signals back to human hands. They developed pressure gauges, light sensors, radiation detectors, and timing circuits that could capture a fleeting signature before being destroyed. Some devices were buried or shielded. Others were placed at careful distances and connected by long cables. The goal was not just to see a big explosion. The goal was to learn whether the implosion behaved as predicted and whether the nuclear reaction began at the intended moment. This work turned the desert into a temporary laboratory, scattered with equipment that would be sacrificed for data. It also shows something deeply modern. The project did not only build a weapon, it built a new way to do science, where experiments were too violent to repeat casually, so every measurement had to count. A single test could destroy months of careful calibration in an instant. Testing explosives at this level is like striking a match beside a workshop full of fine instruments. Crews might spend weeks aligning sensors, checking timing, and calibrating devices against known references. They would protect equipment with housings, place it in the right geometry, and run rehearsals to make sure triggers worked. Then, the shot would happen. In a heartbeat, shock, heat, and debris could tear cables, shatter mounts, and obliterate the very instruments meant to learn from the event. That meant every test carried a strange urgency. You had one chance to record the right signals, and if you missed them, you could not simply repeat the moment without rebuilding the whole setup. The emotional rhythm was intense. Long, careful preparation, followed by violent erasure. This is part of why the project demanded discipline. Data was precious, and every test was both a question and a gamble. The Trinity site was chosen for isolation, not for comfort. Reaching the test location meant long drives over rough roads, through a landscape that offered little shade and even less convenience. The remoteness was the point. If something went wrong, distance would buy time and reduce casualties. It also reduced witnesses, because curiosity is a security problem. Crews built temporary camps, ran power lines, and hauled equipment across open desert that did not care about schedules. Dust crept into instruments and food, and the heat tested everyone's patience. Still, the site gave planners what no city could. It gave room to stage a first-of-its-kind detonation, with observation posts far enough away to survive. The isolation also created an eerie mood. People were preparing to release a force never before unleashed, and they were doing it in a place that felt deliberately forgotten. That contrast made the countdown feel even more unreal. The first test tower held a device nicknamed the Gadget. The nickname sounded casual, almost playful, which helped people speak about something they could barely absorb. The device was lifted onto a tower so the blast could expand in open air, which improved measurements and reduced ground effects. Technicians checked wiring, triggers, and sensors again and again because a small fault could ruin the test or endanger crews. The assembly process demanded careful handling, since the components included high explosives and delicate parts meant to function in a split second. Around it, the tower looked like simple scaffolding, yet it was supporting a turning point in human history. The name also hints at a coping mechanism. When the stakes are overwhelming, people reach for ordinary words. Calling it a gadget gave the team a way to breathe, even as they watched a machine that could rewrite warfare. Above all, the tower was a stage. It raised the device into view, then waited for a light no one could forget. People watched from miles away, wearing dark goggles and tense expressions. In the final hours, observation became a ritual. Some watched from bunkers, others from cars, and many stood outside despite warnings, because curiosity can be stronger than caution. Dark goggles were meant to protect eyes from the initial flash, which could be painfully bright even at great distance. People turned away at the last seconds, then tried to decide when it was safe to look back. In those moments, conversations often stopped. There was nothing left to do but wait and listen for the world to change. The tension had many layers. Some feared failure and wasted years. Some feared success and what it meant. Others feared the unknown details like wind, fallout, and unpredictable effects. The watchfulness itself became part of the story. A few heartbeats of waiting stretched into something larger, because everyone sensed that the test was not just technical. It was a threshold, and they were standing on one side of it together. The blast created a glassy greenish substance later called Trinitite. After the explosion, the desert surface revealed a strange souvenir. Sand and minerals had been heated so intensely that they fused into a glassy crust, sometimes tinted green. It was physical evidence that the fireball had reached temperatures beyond ordinary experience. People later picked up fragments and marveled at their texture, then learned that even this glass could hold radioactive residues. The substance became a symbol because it turned an invisible process into something you could see and hold. It also raised unsettling questions. If the ground could melt and reform in an instant, what else could be transformed? The formation of Trinitite showed how nuclear detonations do not merely destroy. They remake materials at the molecular level, creating new structures and new hazards. It was an accidental artifact, created without intent, yet it became a lasting reminder that the environment itself had been altered. The desert kept the receipt. Shockwaves broke windows far away, even with warning zones. The test planners drew safety circles and established distances, yet the physics of a large blast has its own reach. The pressure wave expanded outward, and it carried enough force to rattle structures and break glass at surprising distances. People in nearby areas reported a sudden thump, then a delayed roar, and then the uneasy realization that something enormous had happened beyond the horizon. This mattered for more than drama. It showed how difficult it is to contain effects that move through air. Even if you keep people away, you cannot keep the atmosphere from transmitting energy. The window breakage also produced rumors, and rumors threatened secrecy. Officials had to manage questions without revealing the truth, which meant inventing explanations that sounded plausible. The far-reaching shockwave became an early lesson in nuclear scale. A device can be tested in isolation, yet its signature can still announce itself to the wider world. The blast did not stay politely inside the fence line. The fireball was brighter than any sunrise most witnesses had seen. When the device detonated, the first impression was light, not sound. Witnesses described a sudden brilliance that seemed to flood the entire landscape, turning night into something harsher than day. That brightness was not gentle like morning. It was intense, immediate, and hard to look at, even through protection. The flash revealed how quickly energy can appear when nuclear reactions run away, converting a small amount of mass into heat and radiation. People had prepared themselves intellectually, yet brightness like that is hard to imagine until it happens. The light also changed emotions. Some felt triumph because the design worked. Others felt dread because the light made the power feel personal. The fireball's color and shape shifted rapidly, and it left after images in eyes that had looked too long. In that moment, the project stopped being plans and calculations. It became a sensory fact. A sunrise is expected. This light felt like a warning that arrived without asking permission. Some observers described the silence just before the sound arrived. There is a strange gap in big explosions. Light reaches you first. Then you wait for the air to carry the sound. At Trinity, that gap became unforgettable. People saw the flash, then stood in a quiet that felt unnatural, because their bodies expected a roar that had not yet reached them. During that pause, time seemed to stretch. Some held their breath. Some spoke without meaning to, then stopped again. The delay made the blast feel distant and intimate at the same time. Distant because it was far away. Intimate because you could sense the wave approaching through anticipation alone. When the sound finally arrived, it came as a deep roll that shook the ground and chest, reminding everyone that the atmosphere was now delivering the second half of the event. That pattern of flash, pause, and impact became a signature of nuclear detonations. It also became a metaphor people carried forward. Consequences can lag behind decisions, even when the decision itself is instantaneous. Trinity gave them a lesson in that delay. The mushroom cloud climbed rapidly, carried by heat and rising air. After the initial flash, the sky began to rearrange itself. Superheated air rose quickly, pulling dust and debris upward, and cooler air rushed in underneath to replace it. That circulation shaped the cloud into a column with a swelling top, which became the visual icon people later associated with nuclear weapons. Watching it build was like watching weather form in minutes, except this weather came from human design. The cloud's height and shape also mattered scientifically because it influenced how material was dispersed. Observers tracked it carefully, noting direction and growth, since wind patterns could turn the spectacle into a hazard. The sight had a psychological punch too. A cloud is usually a sign of nature. Here it was a sign of invention, and it rose with a speed that made it feel alive. The rapid climb showed that the event was not finished when the flash ended. The atmosphere continued to respond, like a bell still ringing after it has been struck. Scientists measured fallout patterns with planes and ground teams. Once the explosion happened, the next urgent question was where the radioactive materials would go. Teams used instruments on the ground, and some flew aircraft to sample the air and track dispersal. This work blended bravery with procedure. Pilots and technicians followed planned routes, carried detectors, and returned with data that would shape safety decisions and future tests. On the ground, crews mapped readings and compared them to wind forecasts because prediction mattered as much as measurement. The challenge was that fallout is invisible, and early detection tools were still evolving. Scientists had to translate clicks and readings into maps that people could act on. This was not only about protecting test personnel. It was also about learning what the bomb did to the environment and what limits might be possible in later operations. The measurement effort was part of a new scientific reality. Nuclear weapons created hazards that traveled, persisted, and ignored human boundaries. The project had to become expert in tracking an enemy it had created. The test confirmed implosion, but it also unleashed new moral dread. Technically, the test answered its biggest question. The implosion approach worked, and it worked decisively. That success produced relief, pride, and a rush of urgency about what could come next. Yet the same moment also forced a different kind of reckoning. People who had spent years solving puzzles now faced what their solutions could do to human beings and cities. The weapon was no longer hypothetical. It had proven itself in light, pressure, and radiation. That proof changed the emotional landscape inside the project, even if not everyone spoke about it openly. Some felt they had ended a war faster. Others wondered what they had invited into the world. The dread was not only about immediate use. It was about what the existence of the weapon would do to politics, fear, and future wars. Trinity was a scientific milestone, and it was also a moral pivot. The project had crossed from possibility into reality, and reality is harder to hide from your conscience. Los Alamos recruited minds from around the world, many fleeing war. People arrived with accents, notebooks, and half-finished ideas, and they stepped into a place that barely existed yesterday. Some had crossed oceans with little more than a suitcase. Others had left comfortable careers because the war had made comfort feel temporary. Recruiters searched for anyone who could solve hard problems fast, from theoretical physicists to explosives experts to instrument builders. At Los Alamos, a hallway conversation might include a Nobel-caliber idea and a practical fix for a stubborn machine. The mixing of backgrounds mattered, because the work demanded fresh thinking from every angle. It also created an unusual community, where brilliance sat next to uncertainty about the future. Many newcomers could not tell friends where they were, and they could not explain what they were doing. Yet they kept coming, because they believed their skills might shorten the war, and because the project promised a chance to shape history directly. Refugee scientists brought urgency, because they knew what fascism could do. For some scientists, the threat was not abstract strategy. It was memory. They had seen universities purged, neighbors vanish, and governments use ideology to crush whole lives. That experience turned the project into something personal. It was not only research. It was a desperate attempt to prevent a nightmare from winning. Many refugees carried grief alongside their expertise, and that grief sharpened focus. They pushed for speed, they argued fiercely, and they worried about delays that others treated as normal scientific caution. Their urgency also shaped the tone of the lab, because it reminded everyone that the war was not distant from the chalkboard. Even when they joked or shared meals, the stakes were never far away. This is one of the most human dimensions of the program. The push to build the bomb did not come only from patriotism or ambition. For many, it came from the fear of what a brutal regime might do with the same knowledge. Some families lived in cramped housing, with rationing and shared walls. Daily life at Los Alamos was not glamorous. Families squeezed into small spaces that were built quickly, and privacy could feel like a luxury. You might hear your neighbors through thin walls, and you might borrow supplies because the store shelves were limited. Rationing shaped meals, clothing, and small comforts, and it reminded people that the war touched even this hidden town. Children played in dusty streets while their parents worked on problems that could change the world. That contrast could feel surreal, because a swing set and a top-secret briefing might exist within the same afternoon. The cramped housing also created social pressure. When you cannot escape your community, every disagreement lingers, and every friendship matters more. Yet the closeness could also produce warmth. People shared food, shared news, and shared the quiet understanding that nobody else outside the fences could fully grasp their strange new home. The town had schools, shops, and mail, yet remained absent from mats. Los Alamos had the rhythm of a real town. There were classrooms, a small store, places to pick up necessities, and routines that made life feel steady. At the same time, it was meant to be invisible. Maps did not show it clearly, and most Americans could not have pointed to it if asked. That invisibility did not only protect secrets, it altered identity. Residents lived in a place that felt both ordinary and unreal, like a stage set built for one purpose. You could attend a school meeting, then pass a guard post on the way home. You could buy groceries, then see soldiers monitoring the roads. The hidden town also shaped how people spoke, because they learned to avoid details that might reveal location or mission. This combination of normal civic life and deliberate erasure is part of what makes Los Alamos so fascinating. It was a community built to function, but also built to vanish in the public imagination. People used P.O. boxes to hide where they actually lived. Mail became a careful performance. Instead of writing a real street address, many residents used post office boxes that concealed the town's identity. That meant even simple correspondence carried a layer of disguise. A letter to a relative might look ordinary on the outside, yet it represented a life lived behind fences. The system protected location, but it also created distance. People could not describe their surroundings, and they could not share the everyday stories that make families feel close. Some learned to write around the silence, focusing on weather, health, or vague hints about busy work. The P.O. box became a symbol of compartmentalization. You had a public self that could send and receive letters, and a private self that could not say where the letter came from. This detail sounds small, yet it shows how secrecy reached into the most human spaces. Even affection had to travel through a mask. Letters were censored, and long-distance calls drew suspicion. Communication was treated as a possible leak, so it was watched. Letters could be inspected, and anything too specific could be removed or questioned. That changed how people wrote, because they learned to avoid names, avoid details, and sometimes avoid writing at all. Phone calls carried their own tension. Long-distance calls were not routine, and a call could attract attention simply because it was unusual. People planned conversations like they planned experiments. What can I say? What must I not say? How do I answer questions without revealing anything? This constant filtering created emotional strain because secrecy does not only hide facts, it restricts comfort. If you are worried or exhausted, you cannot freely vent to a friend far away. You must stay vague, even when you need clarity. The atmosphere of suspicion also shapes self-control. A careless phrase could bring consequences, so people learned to speak in careful shapes, as if every sentence might be overheard. Even friendships were shaped by what you were allowed to mention. In most towns, friendship grows through shared stories. Here, stories had locked doors. You might like someone, eat dinner with them, and still have no idea what they did all day. You learn to bond through safe topics, like hiking trails, music, children, and the small dramas of supply shortages. Sometimes two people worked on related problems, yet they could not connect the dots aloud. That created a special kind of intimacy and frustration. Intimacy because you sensed you were part of something immense together. Frustration because you could not fully share your own life. It also created strange social boundaries. You might trust someone personally, yet still be forbidden to tell them what you knew. This shaped the town's emotional texture. People could feel close and lonely at the same time. It is one of the quiet costs of secrecy, that it reshapes relationships into careful fragments. Still, friendships formed, and many endured, because humans find ways to connect even when language is restricted. A security clearance could vanish overnight, leaving lives abruptly uprooted. In Los Alamos, permission was power. A clearance determined where you could work, what you could read, and whether you could remain at all. If concerns arose, the decision could be swift. One day you were inside the mission. The next day you might be escorted out, with little explanation and no chance to argue. That possibility created a background anxiety, because it meant your career and your family's stability could hinge on unseen evaluations. People watched their behavior, their conversations, even their associations, knowing that suspicion could travel faster than facts. The human impact was sharp. If someone lost clearance, their spouse might lose a job too, and their children might have to leave school and friends immediately. The secrecy that protected the project also protected the reasons behind these decisions, which made them feel even harsher. This is a dramatic reminder that the Manhattan Project was not only science under pressure. It was life under rules that could change without warning. Scientists held seminars while military police guarded the doors. Even in a secret lab, knowledge had to move, so seminars became essential. Scientists gathered to share results, debate methods, and challenge assumptions. Yet the setting was unlike any university. Guards stood nearby, and access was controlled, which meant the usual openness of academic life was replaced by an atmosphere of constraint. That created a strange tension in the room. Ideas needed freedom, but the environment emphasized control. Speakers had to judge what could be said to whom, even inside the same building. Still, those seminars could be electric. A new calculation could save weeks of work. A sharp question could expose a hidden flaw. People listened hard because time mattered. The guarded doors also carried symbolism. It was learning under lock and key. The project showed that even the most secret work still depends on conversation, and conversation depends on trust. The guards were there to protect a mission, yet the mission also relied on the fragile human act of sharing thoughts out loud. A single colloquium could change the entire direction of an experiment. Sometimes the biggest shift came from one talk. A researcher might present a puzzling result, and within minutes, someone else would recognize the pattern and suggest a new approach. An experiment could be redesigned on the spot, not because of authority, but because the room's collective insight suddenly clicked. These moments mattered because resources were limited and deadlines were brutal. If a colloquium revealed that a method was flawed, it could prevent weeks of wasted work. If it revealed a smarter test, it could accelerate progress dramatically. The atmosphere could be intense. People interrupted, challenged, and refined ideas in real time because politeness was less important than clarity. In a normal setting, that might feel harsh. Here, it could feel necessary. The fascinating part is that history often turns on such small gatherings. A room, a chalkboard, a handful of minds, and a new direction chosen in an hour. The Manhattan Project had plenty of massive construction, yet it also depended on these compact moments of shared thought. The project produced its own slang, blending physics and army procedure. Words became tools, because plain language was often too risky or too clumsy. Scientists and soldiers shared the same hallways, so vocabulary began to mix in surprising ways. A theoretical discussion might end with a crisp status update that sounded like a field report. A technical failure might be described with a nickname that made it feel less frightening, which helped people keep working. Codenames shaped speech too, since real places and real materials were not always safe to say out loud. Over time, this created a dialect that newcomers had to learn quickly if they wanted to follow conversations. The slang also revealed emotion. Humor showed up in odd places, and it acted like a pressure valve for stress. In a town built around secrecy, a shared shorthand gave people belonging. It let them communicate fast, stay guarded, and still feel like a community inside a mission that rarely allowed anyone to speak plainly. Many calculations were done by human computers with desks and hand tools. Before sleek machines took over, calculation was a human job with ink, paper, and immense patience. Teams of people worked through long chains of arithmetic, checking one another because a small mistake could mislead a whole design. They used desk calculators, slide rules, and carefully organized worksheets, and they developed routines that kept errors from creeping in during late hours. The work could feel like building a bridge out of numbers, one span at a time. Some problems required repeating the same procedure again and again, then comparing results to see whether a change in one assumption shifted everything. These computers were essential because the physics demanded quantities, not just ideas. Their efforts turned chalkboard concepts into tables that engineers could trust. It is easy to picture the project as flashes of genius, yet much of it was persistence. Quiet rooms filled with focused people, turning pages, listening to pencils, and transforming uncertainty into usable answers. Early electronic computing helped with simulations, still primitive by modern standards. As demands grew, the project began leaning on early electronic machines that could handle repetitive tasks faster than a room full of people. These systems were limited, temperamental, and nothing like modern computers, yet they offered a new advantage. They could run the same kind of calculation many times without fatigue, which mattered when you needed to explore many scenarios. Setting up a run required careful planning because you could not casually change inputs and instantly see results. People had to think ahead, prepare data, and translate mathematical problems into the machine's language and constraints. When it worked, it felt like a small miracle. When it failed, it could eat days. This early computing was not a replacement for human insight. It was an amplifier for it. It let teams push further into complex behavior, and it quietly previewed a future where wars and research would increasingly depend on machines that could model the unseeable. Neutron diffusion tables guided designs like maps through invisible terrain. Neutrons do not leave tracks, yet designers needed to know where they would go. Diffusion tables became a way to navigate that invisible world. They compiled results from theory and experiments, turning neutron behavior into numbers that could be consulted, compared, and trusted. An engineer could use them the way a traveler uses distances and landmarks, even though the lander was a cloud of probabilities inside metal and explosives. These tables helped answer practical questions. How quickly might neutrons leak away? How much material was needed to keep the reaction growing? How would surrounding components affect the balance? The tables also carried urgency because they were built under wartime deadlines and improved as new measurements arrived. A revision could shift confidence overnight. What makes them fascinating is their humility. They are not dramatic like a test blast, yet they were essential. They guided decisions that no human senses could confirm directly, and they helped transform nuclear physics into a design that could actually be built. Metallurgists fought plutonium's strange phases because it changed shape easily. Plutonium refused to behave like a friendly engineering metal. It could change crystal structure with temperature shifts that seemed small, and those shifts could change density and dimensions. That meant a carefully machined piece might not stay the same shape when conditions changed, which is a nightmare when precision matters. Metallurgists had to learn its personality quickly, even though it was hazardous to handle and available only in limited amounts. They studied how it responded to heat, how it cracked, and how it interacted with other materials nearby. This work required both science and craft because the metal's behavior had to be tamed enough for reliable manufacturing. The struggle also forced the project to respect materials science as much as theoretical physics. A design can be perfect on paper, yet it fails if the metal itself will not cooperate. Plutonium made that lesson unavoidable, and it turned metallurgists into quiet heroes of the program. Special alloying helped stabilize plutonium into a workable form. One breakthrough came from treating plutonium less like a single material and more like a recipe. By adding small amounts of another element, metallurgists could encourage it to stay in a more stable phase at practical temperatures. That stability mattered because it made parts easier to machine, easier to measure, and more predictable over time. The choice of alloying element, and the exact amounts were not casual decisions. Too much could introduce new problems, and too little could fail to solve the original one. Teams had to test samples, compare properties, and confirm that the improved behavior held up under the demands of assembly. This was a subtle kind of ingenuity. It did not rely on bigger machines or louder tests. It relied on understanding how atoms arrange themselves in solids, then nudging that arrangement toward reliability. The result was a piece of metal that behaved less like a living creature and more like an engineered component, which helped the implosion design move from theory into hardware. Machining radioactive metal required glove boxes and relentless cleanliness. Working with dangerous metal demanded a barrier between human skin and contaminated dust. Glove boxes provided that barrier, sealing the work area while operators used built-in gloves to cut, shape, and measure. Inside the box, every tool had to be chosen carefully because tiny metal shavings could spread contamination. Cleanliness was not a matter of pride. It was protection. Airflow, filters, and procedures helped keep particles from escaping into rooms where people ate, talked, and breathed. The work was also physically awkward. Fine movements are harder through thick gloves, and fatigue builds quickly when precision is demanded. Yet the parts had to meet strict tolerances, so the craft had to remain steady. This environment changed the feel of manufacturing. A normal machine shop is noisy and open. Here it was sealed, cautious, and methodical. It is a striking image of the atomic age being built, not only with bold ideas, but with careful hands working behind glass. Criticality accidents were a constant fear in rooms full of fissile material. When enough fissile material is brought into the wrong arrangement, it can start a chain reaction without warning. That possibility haunted laboratories where people handled pieces, experiments, and assemblies. The danger was not a large explosion like a bomb. The danger was a sudden burst of radiation, intense enough to injure or kill before anyone understood what had happened. That made geometry and procedure feel like life and death. Distance mattered, spacing mattered, and even the choice of tools could matter if they reflected neutrons back toward the material. Workers relied on rules, alarms, and experienced judgment, yet fear remained because no one had centuries of experience to lean on. In some rooms, the atmosphere was quiet but tense, as if the objects on the table were listening. This fear shaped habits. People double-checked arrangements, moved slowly, and respected limits that seemed picky to outsiders. The project was racing to finish, yet it had to avoid accidents that could stop everything instantly and permanently. One famous accident killed a scientist after a slip during a risky demonstration. Some experiments were so close to the threshold that they demanded perfect attention. In one notorious case, a scientist was demonstrating a critical assembly method when a tool slipped, briefly creating a configuration that released a deadly N-gas. Radiation burst. The room did not explode, and there was no dramatic fire. The danger arrived silently, through invisible particles. The immediate shock was confusion, then the slow, grim realization of what the exposure meant. Colleagues tried to help, and the scientific community absorbed a lesson that was hard to forget. This tragedy was not just a personal loss. It became a warning about bravado and routine, and about how small mistakes can be catastrophic in nuclear work. It also revealed the human pressure inside the project. When time is short, people take risks they would avoid in calmer years. The accident stands as a reminder that the line between controlled experiment and lethal event can be thinner than anyone wants to admit, especially when the material itself cannot be seen. Safety rules tightened, but the pressure to finish never truly eased. After accidents and close calls, procedures grew stricter. Limits were clarified, checklists became longer, and supervision increased in the most dangerous areas. Yet the project's schedule did not loosen its grip. The war still demanded speed, and leadership still demanded results, so workers lived inside a constant compromise between caution and urgency. That tension shaped daily choices. Do you pause to verify again? Or do you move forward? Because a delay affects everything downstream. People learn to respect safety while still feeling chased by time. In some places, rules became a kind of language of care, a way to protect colleagues without slowing progress more than necessary. In other places, stress made compliance harder because exhaustion erodes attention. What makes this fact compelling is its realism. There was no moment when the project became comfortable. Even improvements carried weight because they were layered onto a mission that kept accelerating. The work continued with sharper rules, sharper nerves, and the same relentless expectation that the outcome must arrive before history moved on without it. The project relied on vast quantities of silver for electrical conductors. When copper became scarce, the project turned to a metal that most people associate with jewelry and coins. Silver carries electricity extremely well, which made it valuable for high-current equipment that could not tolerate losses. The surprising part was how much was needed, because the machines were huge and their currents were relentless. Designers had to think in tons, not in grams, and they needed conductor shapes that fit into coils and bus bars without overheating. Using silver also raised a psychological bar. It signaled that the program could reach into a nation's most guarded resources, if it had to. Workers shaped and installed these bright conductors inside industrial systems that were never meant to be glamorous. The metal did not make the work pretty. It made the work possible. That twist is pure Manhattan Project. Luxury materials were pulled into a grim task, because physics does not care what a substance feels like in your hand. Silver borrowed from the treasury replaced scarce copper in key machinery. In a wartime economy, even wiring became a strategic problem, and the solution was astonishingly direct. The government arranged for silver reserves to be loaned out for industrial use, then tracked and demanded its return afterward. This was not symbolic. It was practical engineering under pressure. The silver was formed into conductor components, installed in critical machines, and treated like borrowed treasure that could not be wasted. Every piece had to be accounted for, because the metal belonged to the public even while it served a secret mission. That accounting created its own discipline. Inventory lists mattered, scrap mattered, and recovery mattered when equipment was replaced. It is a wonderfully strange image. The same kind of metal that sat behind national confidence in currency was rooted into humming devices that separated atoms. The project did not only build new technology, it rearranged priorities so thoroughly that the line between finance and physics briefly dissolved. The supply chain stretched worldwide, including uranium from the Belgian Congo. The project's raw material was global because the best ore was not conveniently located near the laboratories. One major source came from mines in the Belgian Congo, where uranium-rich rock had been extracted long before most people imagined an atomic weapon. This meant diplomacy, shipping, and secrecy had to work together. Contracts had to be made quietly, shipments had to move across oceans, and storage had to be secure once the ore arrived. The material itself became a geopolitical object, not just a mineral. Decisions made in distant places now influenced the pace of a hidden American program. That reach adds a powerful perspective. The bomb was assembled in specific sites, yet its ingredients were gathered across continents. It was built from an international footprint that most workers never saw. In that sense, the Manhattan Project was not only a national effort, It was a global extraction and transport story, pulled tight by wartime urgency. Railroads moved components that looked ordinary, yet were profoundly dangerous. A train car can carry many things that appear harmless, and that normal appearance was part of the protection. Crates and drums rolled along rail lines with labels that did not reveal their true value, and many rail workers had no reason to suspect anything unusual. Yet some cargo had extraordinary implications. It might be a specialized part that only one plant could manufacture. It might be a chemical feedstock whose delay would stall an entire process. It might even be material that demanded careful handling because of toxicity or future radioactivity. Scheduling mattered because rail networks were crowded with wartime traffic, and a missed connection could ripple into weeks of lost momentum. Security often relied on quiet coordination rather than spectacle, because drawing attention was its own hazard. This creates a fascinating contradiction. One of history's most secret and consequential programs moved through the same rail corridors used for mail and groceries. The difference was hidden inside the box and in the guarded urgency of those who tracked it. Military couriers carried documents handcuffed to wrists in some deliveries. For some information, physical paper was treated like a weapon. Couriers were trusted to move documents between sites, and sometimes the precautions were dramatic, including keeping briefcases literally attached to the courier's body. The goal was simple: prevent loss, theft, or casual copying. These trips were not glamorous. They were tense, repetitive, and often lonely, because a courier could not chat freely about where they were going or why. Routes could be planned with security in mind, and stops were minimized. Even a restroom break became a moment to manage carefully. The remarkable part is what those papers represented. They could be design details, production numbers, or test results that saved months of work. A sheet of typed text could change engineering decisions across the country. In a world before easy encryption and instant communication, the courier became part of the system's nervous network. The handcuffs were not theater. They were a blunt recognition that ideas can be as dangerous as explosives. Camouflage stories explained strange construction to nearby communities. When massive buildings rise quickly, people notice, and questions follow. To protect secrecy, officials crafted cover stories that sounded ordinary enough to accept, yet firm enough to end curiosity. A new plant could be framed as a conventional munitions effort, a chemical facility, or an engineering project tied to the broader war. Workers repeated these stories at home, often without being told that they were repeating a story at all. This kind of camouflage was social engineering. It relied on human habits like politeness and patriotism, because during wartime, many people did not push too hard once they heard military. The cover stories also had to be consistent across different audiences, because contradictions spread quickly in small communities. This adds a subtle layer of intrigue. Secrecy was not only fences and guards. It was narrative control. The project built physical structures at unbelievable speed, and alongside them, it built explanations that could travel just as fast, smoothing suspicion before it could harden into investigation. Codenames like Site Y made a sprawling program sound deceptively small. A codename can shrink something in the mind, and that shrinking was useful. Site Y sounds like a minor outpost, not a town full of scientists trying to solve world-altering problems. The beauty of these labels was their blandness. They offered no meaning to outsiders, and they allowed insiders to speak quickly without revealing location or function. Codenames also supported compartmentalization, because you could know Site Y and still not know what happened at Site X. This language shaped planning documents, phone calls, and everyday conversation, so it became a kind of second geography that only insiders could read. The irony is that the project was enormous, yet it hid behind names that felt like filing cabinet categories. That mismatch was part of its success. A gigantic effort can become less visible when it is described in small, abstract terms. The program's true scale lived in concrete and cables. Its public shadow lived in a letter and a dash. Workers signed secrecy oaths that could follow them for life. From the beginning, many workers were required to promise silence, not just during the war, but indefinitely. Signing an oath was a serious act because it turned curiosity into risk. It also created a lasting psychological boundary. You could leave the job, move to another state, and still carry the same invisible rule inside your daily life. Some people learned to dodge questions with practiced vagueness, even years later. Others found that the habit of silence became part of their personality because it had been rehearsed so often. The oath also reinforced hierarchy. Those who knew more carried heavier responsibility, and those who knew less were still warned that talk could bring consequences. This legal commitment was part of how the project maintained control across vast distances and thousands of people. It also left a quiet legacy. After the war, many families realized that a loved one had lived through extraordinary events and could not fully share them. The secrecy did not end with the job. It traveled home in the shape of unsaid sentences. Newspapers were kept uninformed, even when rumors started to spread. In an era when major projects often produced headlines, this one produced silence. Editors heard whispers about strange towns and huge plants, yet official channels offered nothing solid, and wartime caution discouraged aggressive digging. The government also had tools to manage information flow, and reporters understood that pushing too hard could be framed as unpatriotic during a national balm. Emergency. Still, rumors are restless. Workers talked in fragments. Construction crews noticed scale, and local communities pieced together partial stories. The press remained largely locked out, which meant the public had no context for the enormous effort unfolding inside their own country. That absence is part of what made the later reveal so shocking. When information is withheld, imagination fills the gap, and imagination often guesses wrong. The Manhattan Project was a case study in controlled ignorance, not because journalists were incompetent, but because the system was designed to keep them chasing shadows. It was one of the rare moments when a program of immense consequence operated almost entirely outside the day's headlines. The first public explanation came only after the bombs were used. For years, the project existed as a hidden machinery of construction, research, and guarded labor. Then, after the weapons were dropped, the public suddenly faced words like atomic energy and uranium in a new and terrifying context. The explanation arrived not as a gradual disclosure, but as an aftershock, because people were learning about the program at the same time they were learning what it had done. That timing shaped reactions. There was awe at scientific achievement, grief at destruction, and fear about what might come next. It also meant the workers' silence ended in a strange way. Many could finally say what they had been part of, yet they were saying it into a world already changed by the result. The delayed disclosure is a reminder of how tightly the program was sealed and how decisive the reveal was. This was not a secret that faded into history. It erupted into public life in one blunt moment, and the conversation it started has never fully ended. Intelligence efforts hunted German progress, sometimes chasing shadows and misinformation. The fear of a German atomic weapon created a second war that was fought with rumors, intercepted reports, and frantic interpretation. Analysts tried to read meaning in purchases of heavy water, in movements of scientists, and in any hint of unusual construction. Some leads were solid. Others were traps, exaggerations, or misunderstandings that burned time and attention. What made it so tense was the uncertainty. If you underestimate the enemy, you might lose the war. If you overestimate, you might commit resources to a nightmare that is not real. This hunt shaped priorities, because every scrap of intelligence could influence funding and urgency back in the United States. It also produced a strange emotional climate. Scientists felt both needed and haunted, because the motivation for their work was a threat that might be advancing in secret. In that atmosphere, even a false clue could feel like an alarm bell that must be answered. The ALSO's mission followed the front lines, grabbing papers and scientists. As Allied forces moved through Europe, a specialized team moved with them, hunting for evidence of German atomic progress. They searched laboratories, seized documents, and questioned scientists, sometimes within days of a town changing hands. Speed mattered because knowledge is easy to hide or destroy when defeat is near. They also had to make fast judgments under chaos. Is this equipment ordinary? Is this research relevant? Is this person important, or just nearby? The mission was part detective work and part battlefield logistics. It required translators, scientific expertise, and the ability to operate amid uncertainty and danger. The most gripping detail is how physical it was. Ideas that could reshape the world were carried in folders, notebooks, and hurried interviews. The effort was not only to learn, it was to prevent knowledge from being scattered into the wrong hands at the end of the war. In a conflict defined by machines, this was a chase for minds and paper. Captured German resources showed the feared Nazi bomb program was behind. When evidence finally came into clearer focus, it suggested a sobering twist. The terrifying vision of an imminent German bomb did not match the reality on the ground. Resources were fragmented, leadership was inconsistent, and key materials and organization were not in place at the scale needed. For the Manhattan Project, that revelation carried mixed feelings. It brought relief, because the race looked less like a photo finish. It also brought a sharp question. If the enemy was not as close as feared, why had the Allies pushed themselves into such an extreme sprint? The answer is complicated, because wartime decisions are made without perfect information. Still, the discovery reframed the story. The project did not only respond to proven danger, it responded to imagined danger that felt real enough to act on. That is a powerful lesson about intelligence and fear. Once a nation believes a threat is possible, it may build an answer that changes history, even if the threat was never truly near completion. Meanwhile, Soviet intelligence gathered details through both ideology and opportunity. While the project guarded its secrets, another network looked for openings in human nature. Some sources were motivated by ideology, believing power should be balanced so no single nation could dominate. Others were motivated by personal ties, money, or the simple fact that wartime alliances created contact that could be exploited. Soviet intelligence used patient methods, building relationships, using intermediaries, and collecting small pieces that added up over time. They did not always need blueprints. Production insights, scientific conclusions, and design logic could save years of trial and error. This effort reveals a truth that is uncomfortable for any secret program. The strongest walls are still made of people, and people have beliefs, fears, and private reasons. The story also adds global context. The Manhattan Project was not only a scientific and military achievement. It was the beginning of an international struggle over nuclear knowledge, where information became a strategic resource as valuable as any metal. Klaus Fuchs passed key information, accelerating another nation's bomb effort. He was a brilliant physicist within the project, trusted with sensitive work, and he chose to share secrets with the Soviet Union. His role mattered because he had access to high-value understanding, not just scattered trivia. Information about design approaches and scientific reasoning can compress a competitor's timeline, removing dead ends before they waste effort. What makes his case so unsettling is how ordinary he could appear in daily life. He attended meetings, contributed ideas, and moved through the same guarded spaces as everyone else. The betrayal was not visible in the uniform or a loud act. It was quiet, repeated, and methodical. After the war, revelations about his espionage shook confidence in the project's security model, because it showed that clearance and competence are not the same as loyalty. His story also forces a moral question. Some argue he helped prevent monopoly power. Others see an unforgivable breach that fueled a dangerous arms race. Either way, his actions changed the pace of nuclear history. Espionage revealed that secrecy can be pierced, even by tight security. The Manhattan Project built fences, controlled language, and compartmentalized information with intense discipline. Yet espionage still happened, which revealed a hard truth about secrets in large organizations. Secrecy is not a single lock. It is thousands of daily decisions made by people who get tired, fall in love, believe in causes, or underestimate risk. A single conversation overheard, a document copied, or a trust misplaced can bypass layers of protection. The project's size made it vulnerable because the work required many specialists, and specialists need access to do their jobs. This creates a permanent tension. If you restrict too much, progress slows. If you share too much, the secret leaks. The lesson traveled far beyond the war. It influenced later security culture in government and science, and it helped define the Cold War atmosphere of suspicion. The deeper point is almost philosophical. Knowledge wants to move, and determined networks can help it move, even when rules insist it must stay still. After the war, questions of loyalty reshaped American science and politics. Once the immediate emergency passed, the nation turned inward and asked who could be trusted with world-ending power. Scientific institutions that had thrived on open exchange faced new restrictions and new scrutiny. Investigations, hearings, and background checks became part of the landscape, and suspicion could attach to friendships, past affiliations, or unpopular opinions. For many scientists, this felt like a betrayal of the very culture that made progress possible. For many officials, it felt like necessary defense in a new era. The result was a complicated reshaping. Research became more tied to national security, careers could hinge on political wins, and public debates about communism and patriotism spilled into laboratories and universities. This loyalty pressure also changed what young scientists chose to study, because some fields became entangled with secrecy and risk. The Manhattan Project had proven what science could do with money and urgency. The post-war period showed what fear could do to science itself, altering norms of openness, trust, and intellectual freedom. Oppenheimer later lost his clearance, despite leading the project to success. After the war, he became a public symbol of the atomic age. Yet he also became a target in the growing conflict over nuclear policy and perceived loyalty. His views on future weapons and his earlier associations were examined in a highly charged environment, and the process turned personal and political at the same time. Losing clearance was not a minor administrative shift. It meant losing official trust, losing influence on policy, and watching your name become a battleground. For many scientists, the case felt like a warning. If even the project's scientific leader could be cast aside, then nobody was safe from suspicion. For others, it was framed as a necessary act of security, meant to protect a nation entering a new rivalry. The episode reshaped how the public understood scientific authority. It showed that expertise does not guarantee political protection, and that the people who build powerful tools can later be judged by standards that have little to do with their technical achievements. Some scientists became activists, urging international control of nuclear weapons. For many who had helped create the bomb, the first post-war years brought a new mission. They argued that nuclear weapons were too destructive to be managed by ordinary rivalry, and they pushed for international oversight, treaties, and shared rules that could prevent catastrophe. Some wrote public essays, some advised policymakers, and some formed groups that tried to educate citizens about the stakes. Their activism was not uniform. It ranged from cautious proposals for regulation to urgent warnings about an arms race. What united them was a sense of responsibility because they understood the weapon's power from the inside. This movement also created friction. Critics accused them of naivety or disloyalty, while supporters saw them as voices of conscience. The struggle was not only about policy. It was about the role of scientists in society. Are they builders who step back once a device works, or are they citizens with a duty to speak when their inventions can threaten humanity? Their choice to speak helped shape public debate for decades. Others argued deterrence would prevent war, even while it raised the stakes. Another group looked at the same weapon and reached a darker conclusion. They believed the bomb's horror could become a kind of shield, because fear of retaliation might stop leaders from starting major wars. This logic, called deterrence, treated peace as something maintained by credible threat rather than trust. It demanded readiness, clear signaling, and the belief that rational actors would avoid mutual disaster. The argument had persuasive power in a tense geopolitical world, yet it carried a chilling cost. If safety depends on threat, then accidents, miscommunication, and escalation become permanent dangers. Deterrence also encouraged stockpiles, delivery systems, and planning for scenarios nobody wanted to experience. It reshaped strategy into a psychological game where perception mattered as much as capability. This debate became one of the defining arguments of the modern era. The Manhattan Project created the tool, and the post-war world fought over how to live with it. Deterrence offered a grim promise of stability, paired with an equally grim awareness that stability could fail. The bombs forced leaders to confront surrender, strategy, and civilian catastrophe. In the summer of 1945, the weapon was no longer a laboratory question. It was a decision on a desk. Leaders weighed military goals against moral damage, and they did it under the pressure of a war that had already consumed millions. Some advisors argued that only a shock of unprecedented scale could force surrender quickly. Others warned that the human cost would stain history. Behind closed doors, planning involved target lists, weather windows, and messages meant for both allies and enemies. The civilians in those cities were not abstract numbers, yet they were often discussed through the cold language of strategy. The decision also carried a diplomatic edge, because the post-war world was taking shape even before the war ended. When the bombs were used, the world saw a new kind of catastrophe, and leaders everywhere had to accept that politics had entered an era where a single order could erase a BTAS. Cities' ordinary mourning. Hiroshima and Nagasaki became names that reshaped the meaning of victory. After the war, those two place names stopped being just geography. They became symbols that carried grief, awe, and warning all at once. Victory was no longer only about armies and borders. It was also about what methods were considered acceptable to end a conflict. Survivors told stories of blinding light, sudden heat, and a city landscape turned into silence, and those accounts traveled far beyond Japan. Scientists and soldiers who had celebrated an end to fighting also felt the weight of what had been unleashed. Writers, artists, and educators wrestled with how to describe the event without reducing it to spectacle. Public memory became part of policy because every future nuclear debate returned to these names as evidence. Even people who could not locate the cities on a map learned them as moral reference points. In that way, the war ended, but the argument about what victory meant did not. It continued in speeches, classrooms, and uneasy, quiet moments. The project spurred nuclear reactors for power, medicine, and research afterward. Once a sustained chain reaction had been mastered, people began asking what else it could do besides make weapons. Reactors became tools for producing isotopes used in medicine, including tracers that help diagnose disease and sources used in certain cancer treatments. Research reactors also provided intense neutron beams that could probe materials, study chemistry, and reveal structures that ordinary experiments could not. Engineers explored power generation too, because controlled heat from fission could turn turbines just like coal does, without burning fuel in the usual way. These ambitions grew out of wartime skills, including metallurgy, shielding, monitoring, and large-scale coordination. The strange part is the continuity. The same knowledge that enabled a bomb also enabled hospitals to gain new tools and laboratories to ask new questions about matter. This does not erase the weapon's shadow, yet it shows how a single scientific breakthrough can branch in opposite directions toward both harm and help. It also created enduring environmental legacies at sites like Hanford. Wartime production moved fast, and environmental protection was not the priority it would become later. At large sites, chemical processing and radioactive materials created wastes that were difficult to manage with the tools and understanding of the time. Storage tanks, burial grounds, and disposal choices were often designed for speed, not for centuries. Decades later, those decisions became long-term responsibilities because some contaminants persist and spread through soil and water. Cleanup requires engineering, monitoring, and public trust, and it is expensive precisely because the original work was so urgent. Communities near these sites have lived with complicated feelings, including pride in contribution and concern about health and land. The legacy is also scientific. It has taught hard lessons about containment, record-keeping, and transparency. When people talk about the Manhattan Project's cost, they often think of dollars and wartime labor. The environmental legacy adds another ledger, one written across landscapes that still need care. Declassification later revealed how many near misses occurred behind the scenes. For years, the public saw a clean storyline of success, secrecy, and sudden revelation. Later releases of documents painted a more human picture, full of mistakes avoided, risks accepted, and plans revised under pressure. There were technical surprises that forced redesigns, safety scares that tightened procedures, and management decisions that looked different in hindsight than they did in wartime urgency. Some near misses were mechanical, like equipment failures that could have delayed production at a critical moment. Others were safety-related, where a small error might have harmed workers or damaged confidence. Declassification also revealed disagreements inside the project, including debates over priorities and methods that never appeared in official announcements. This matters because it shows the project as a living process, not a flawless machine. Great accomplishments often include invisible narrow escapes, and secrecy can hide those escapes until decades later. When the curtain lifted, it became easier to see how much depended on judgment, improvisation, and luck alongside brilliance. The project's speed depended on wartime urgency, not normal scientific caution. In peacetime science, you test, verify, and publish with patience. Here, the calendar was treated like an enemy. Teams built facilities while designs were still evolving, and they committed to production methods that were not fully proven because waiting felt more dangerous than guessing. This compressed timeline changed behavior. People accepted higher risks, worked longer hours, and made decisions with incomplete data because the alternative was delay. It also changed relationships between institutions, since universities, industry, and the military had to coordinate without the slow negotiations that usually protect quality. The urgency produced creativity, but it also produced stress, and stress can hide problems until they become crises. The most fascinating part is how deliberate the trade-off was. Leaders understood they were bending normal rules, and they did it anyway because the war demanded it. This helps explain why the Manhattan Project feels so singular. It was not only a scientific breakthrough. It was a unique social and political engine that forced science to move at a wartime pace. It fused academia and industry, creating a template for big science. Before the war, many scientific advances came from small groups with modest budgets. The Manhattan Project showed a different model, where governments could marshal universities, corporations, and military management into one coordinated enterprise. Professors became team leaders. Factory engineers became partners in physics problems. Procurement and construction became as important as theory, because without buildings and machines, the ideas stayed trapped on paper. This fusion created new habits that lasted after the war, including massive funding, classified research, and large facilities dedicated to national goals. It also changed what it meant to be a scientist. You could be brilliant and still need thousands of colleagues and an enormous supply chain to make progress. The project proved that certain problems, especially those involving rare materials and extreme conditions, demand scale. That template later influenced space programs, particle accelerators, and other national research efforts. The legacy is not only the bomb. It is the birth of a new relationship between knowledge and infrastructure, where discovery can require cities, grids, and factories. Its success proved that theory, engineering, and logistics can transform history together. One reason the project worked is that it treated science as a full system. Theory predicted what was possible. Engineering turned predictions into parts that could be built, tested, and assembled. Logistics delivered the materials, power, and people needed to keep everything moving. Remove any one of these, and the effort collapses. Brilliant equations without factories would have meant nothing. Factories without correct theory would have produced useless output. Even the best design would have failed without transportation, scheduling, and reliable supply lines. This is a powerful lesson for understanding modern technology. World-changing tools rarely emerge from a single genius moment. They emerge when different kinds of expertise align under strong coordination. The Manhattan Project created that alignment with unusual intensity, and the result altered global politics in a matter of weeks. It is a reminder that history can pivot not only on ideas, but on the ability to organize those ideas into reality at scale, under pressure, and with pressure. Consequences no one can fully control. The atomic age began with a test flash, then never truly ended. After Trinity, the world could not return to an earlier innocence about war and technology. Even when nuclear weapons were not used, they influenced decisions through threat, fear, and the constant possibility of escalation. Nations built arsenals, developed delivery systems, and treated scientific talent as a strategic resource. Public life changed too. People practiced drills, debated treaties, and absorbed the idea that global destruction could be measured, planned, and prevented only through careful restraint. The atomic age also seeped into culture, shaping films, literature, and the language of anxiety. At the same time, nuclear science expanded into energy and medicine, creating a complicated legacy that is neither purely dark nor purely bright. The reason the age never ended is simple. Knowledge does not disappear. Once humanity learned how to release this energy, the capability became part of the world's permanent furniture. Every generation since has lived with the aftermath of that first flash, whether they think about it daily or only in rare moments of quiet. The Manhattan Project remains a warning about genius, fear, and irreversible tools. The project gathered extraordinary intelligence and creativity, and it achieved what had seemed impossible only a few years earlier. Yet it also shows how fear can accelerate invention faster than wisdom can catch up. When a tool is powerful enough, the moment it becomes real, it changes every future choice. You cannot unlearn the method, and you cannot guarantee that every future leader will be careful. That is the warning. The project story is filled with innovation, sacrifice, and coordination that still amazes engineers and historians. It is also filled with moral weight that does not fade, because the weapon's purpose was destruction on a scale that defies ordinary language. The Manhattan Project teaches that brilliance is not a safeguard by itself. Great minds can build things that outgrow their intentions, and urgent times can reward speed over affection. The lesson is not that science is bad. The lesson is that irreversible tools demand irreversible responsibility, and responsibility is harder to manufacture than hardware. As we come to the end of tonight's journey, just let the scale of it gently settle in your mind. We began in secrecy, with hurried letters and guarded train cars, with mesas transformed into laboratories and deserts chosen for their silence. We walked through humming factories where silver carried current, through reactor halls cooled by wide rivers, and into rooms where calculations were done by steady hands. Sharpened pencils. We stood beneath a test tower in the dark before dawn, watched a flash turn night into something brighter than morning, and felt the long pause before the sound arrived. We followed ideas across oceans, through coded language and hidden towns, and saw how a single decision could reshape diplomacy, science, and the meaning of power itself. The Manhattan Project was not just a machine or a moment. It was people, brilliant, frightened, determined people, working at a pace history rarely demands. It was theory meeting steel, logistics meeting lightning, and conscience meeting consequence. Now, as the story fades, let your thoughts slow with it. Imagine the desert again, long after the test. The wind moves softly across quiet sand. The river at Hanford flows steadily, reflecting the sky. The laboratories are dark, the chalkboards erased, the trains are grist. History continues, but for this moment, everything is still. If you are still awake, there will be another gentle story waiting for you on the screen. You are always welcome to continue the journey with us. And if you found meaning in tonight's exploration, you might consider subscribing or sharing the channel with someone who enjoys these quiet walks through history. For now, let your breathing soften. Let the vastness of it all drift into the background. Sleep well, and good night.